we're going to make it more difficult by not actually showing all the possible options that you could go through and select from. So instead, what we're going to look at is what we have as far as structures go, and then see if we can come up with ways to actually get them to happen. Okay? So let's not stress necessarily about how many steps are involved in each of these. What we want to do is just first start off with the structures that we've got and see if we know of a reaction that would allow us to do that. Remember, reaction type, not reagent. Okay, so which step do you want to look at? We'll call it step 1, red, or step 2, blue. Do either of those stand out as something where you're like, I think that's happening? So in 2 pi bonds attacking the bromines, or both BRs, let's be a little bit careful with that. Okay? How would you expect a pi bond to react?
It says an electron donator.
An electron donor or a nucleophile. How would you expect bromides to react?
Electron donator.
Electron donor. So in your statement, okay, and I understand where you're going with it, but we have to be careful with our language to make sure we don't introduce false thoughts that could mess with our system. You're saying you want the electrons to react with the electrons. Does that work? No. So let's take a step back from that just a little bit, okay, because I like your idea, okay, and let's think of it more as what's changing. What happened to the pi bonds? I have a loss of pi bonds. Technically, I have a loss of 2 pi bonds. What else happened?
You gained 4 sigma bonds.
Okay. We gained some sigma bonds. What sigma bonds did we gain?
2 hydrogen, 2 bromine.
We gained 2 bromine bonds. And then, Anthony, you're jumping in with another statement. What else are you saying?
And we also got 2 hydrogen bonds.
We gained 2 hydrogens. The bromines might be obvious, which is why you might be saying, oh, they attacked the bromines. Where are those hydrogens?
On the other end of the pi bond.
Okay. So that's what we've gained. So within those things that have changed, what kind of reactions have we done?
It's a elimination. Addition.
Okay. Loss of the pi bond is going to be addition. So what we're talking about within this scenario is addition, and in particular, we did 2 additions. Okay. The additions that we added was H and Br. What might be a decent reagent to put in here? Let's throw HBr at it and see what happens. So we can put in HBr. We would expect the pi bond to act as an electron donor, would share with our hydrogen. The electrons would then go to the bromine. The resulting structure, we'd have our pi bond. Our hydrogen would go to the end so that we could form an internal carbocation. And then we would have bromide, Br minus, chilling out there. That Br minus could then go through and react. And we've now done 1 of our additions. I was trying to draw proper geometry and then I'm upset with how I've drawn it, but regardless. And if we had enough HBr, what could happen? We do that whole process again. Okay? So does that match where we would expect our hydrogens and bromines to go? Yeah. Okay? Which means a good reagent 3 would be HBr. Depending on the options, we might have to get more specific and say 2 times HBr because we have to do it twice. Make sense? Okay, cool. So you said you had questions. It's a bit silly. Doesn't sound like you got questions. It sounds like you knew exactly what you needed for that. All right, so now what do you have to do? You got to go to the red. And you do the exact same process. Okay? The first question I asked was what was the chemical reaction? So that was looking at addition. Okay? We didn't start with addition. We started with what things happened. Okay? Theoretically, what you should be doing is recognizing what happened and jumping to that reaction so that you can start processing out reagents. Okay, but it sounds like maybe we need some more work. What things changed from reactant to product for our red arrow?
Double elimination.
Gain 2 pi bonds.
We gained 2 pi bonds.
And lost 4 syntehsis.
This one's going to become a little bit tricky. Okay, so now referencing, you're now jumping out of this what things changed and now telling me the chemical reaction. Okay, and that's probably because you've identified something that's changed. Okay, so far we just said pi bonds, we gained 2 pi bonds. Substitution has nothing to do with gaining 2 pi bonds. Okay, so why are you saying substitution? What's the change that makes you go, I think we got a substitution going on?
Well, the OH is in place of the CH to CH.
I lost the OH, and I've gained 2 carbons. Okay, we could get more specific within this if we kind of color-coded this out. We started with 2 carbons in the OH. We could say that those are maybe those same 2 carbons, and we have gained those 2 carbons. So we could be more specific and say that what we gained was that. Okay. We still have those pi bonds, but if we're saying we gained pi bonds, we've already incorporated it into that. Okay. Depending on what reagents are at our disposal, maybe it is gaining 2 pi bonds. Maybe instead it's more of a substitution. We would have to see what our options were. Okay? So if we push this out and look at those changes, we may see changes, but those changes could come in whole hog as an individual piece. Okay? And that's what you're suggesting, Ivan. So let's go ahead and run with that. Okay? And what you're saying is that we have the loss of the OH and the gain of that new piece. That looks an awful lot like a substitution to you. Okay. We already had the OH. Okay, what is the OH acting as in the case of our substitution? We're saying this is a leaving group. Is OH a good leaving group? That's problematic. Okay, so we may need to fix that. Maybe this is why we have 2 steps, because we have to address that fix first. Okay. Before we start looking into what we change it to, it might be helpful to understand what's going on with our carbons. So in that gaining of those 2 carbons, is that whole hog piece that we're gaining, how did we gain it? What is that reagent specifically acting as? Remember, it's a substitution. Okay? In the substitution, we have 4 component pieces. Leaving group, solvent, I'm trying not to say that, substrate, and our nucleophile. Okay, well, that piece wasn't there to begin with, so it's not our leaving group, it's not our substrate, it's not the solvent, because what we're caring about is what the actual reagents are. Yeah, that makes sense to be the nucleophile. Does that look like a nucleophile yet? No? How would we change that so that structure looks better like a nucleophile? Cool. We could make that a negative carbon. We could also show that hydrogen if we so deemed. Since I'm showing a C there, I feel like I have to show that hydrogen. That's just my kind of personal reflex. So cool, you have a nucleophile. Okay, let's ignore the OH as a leaving group. Could I just add this straight up to this? Could I do that substitution? Right? What would that negative want to do? It's going to find a positive. Where's there a positive? Well, isn't the carbon a positive? I mean, doesn't that work? Yeah, except what does our negative react with? The most positive. And if we look, yes, that carbon is positive, but so is that hydrogen. And so more than likely what would happen is you would get a competition between these 2 reagents. This path would dominate, And what we'd get as a result would be O minus and then acetylene. You don't need to know that, but that's acetylene. Okay? Is that getting us to what we want? No. Okay? And the issue there was that the H of our OH is problematic. We don't like that. Okay? Even if we were okay with it attacking the other carbon, we still encounter this issue of a bad leaving group. Okay? So before we bring in our negative carbon structure, what should we do? We need to make that a better leaving group. We need to make that OH a better leaving group, and we need to make it a better leaving group in a way that doesn't F with the next step of our reagent. Okay? So this helps us out a little bit, because what did we just discover by doing all that work?
What's it next?
Sort of. We know reagent 2. Reagent 2 should be a negative carbon with the triple bond. Okay? So how can I make OH a better leaving group? I could add another hydrogen. So we could add something like H+. Okay? Specifically, that's not a reagent as we talked about last lecture. Okay? But at this point, we're just spitballing to get ideas. Okay? Moving through. The lone pair on our oxygen would come in, pick up the H+. Technically, that would be a green arrow if we're talking about pens that no one's using that I bought for you, but you know, not that anybody's bitter or anything. We'd have a better leaving group, right? Cool, so that fixes that leaving group problem. That's awesome. Now what happens? We would add our nucleophile in, and what happens? So there's an interesting thought. You go, oh, the oxygen is positive. Can the oxygen accept electrons? No. So our nucleophile cannot and never will attack the oxygen. Okay? This goes back to thinking back to review stuff. If we look at H3O+, how does H3O+ react? It donates a hydrogen. And if we draw out the Lewis structure, what atom is positively charged? The oxygen. And yet, what's the chemistry of this? Positive hydrogen, not positive oxygen. Why? The oxygen can't exceed its octet. It's not the one accepting electrons. What it's doing is stealing electrons from the bonds around it. There's the chemistry. So be really careful. Yes, charges are absolutely of critical importance for you to think about their reactivity. But just because an atom is charged does not mean it is the one that is reactive. Make sense? Okay. So where would our negative carbon now come in? What's that?
It takes the hydrogen right off the oxygen.
It reacts with the most positive thing, which in this case is going to be the hydrogen. Did that work? No. So we made a better leaving group, which is great, but that better leaving group is just as reactive, if not more reactive, with our nucleophile. So we need a different leaving group. So let's try it this way. Okay. Let's ignore that we have the OH there. I just want a better leaving group that would actually work with this. What would react best with that negative carbon? What would be a good leaving group? What? Sodium is never a leaving group. What must a leaving group do? Take electrons. What charge is sodium? Positive. Sodium gives up electrons. Sodium will never be a leaving group. It is a counter ion, and we could stabilize this as a reagent and say this is sodium acetylide. That's fine. Okay? But if I put Na on that structure instead of our oxygen, did I make that carbon positive? No, I made it negative. The whole point is to make it positive. What do I put on there that would be a good leaving group? I don't care how I get it. That's irrelevant. What I care about is what's a good leaving group. Bromine would be a great leaving group. Because now what could happen? This could come in, attack, kick that up, ta-da, there it is. Ooh, that would be fantastic. That would be lovely. But that only works if I know the reagent that allows me to convert the OH to the Br. Okay? What's that? Okay. There are a variety of options we could try. We could do HBr. What's going to happen with HBr is the H protonates the oxygen, turning that into a good leaving group. Bromide could theoretically then come into a backside attack and kick out water as a leaving group. Okay? So maybe that could be a reagent. Okay. Could we do Br2? How does Br2 react? It can do radicals, which should already be a red flag. If we're going to say it's doing radicals, we've got a polar bond with the oxygen in there. That structure with our OH, our alcohol, probably isn't going to be running radical reactions. We will absolutely see Br2 as a reagent, and non-radical, it's an electrophile. One of those bromines is electronegative, pulling electrons away from the bromine, making the other one very positively charged. Can we form a bond? Do we have an electron source in our alcohol structure? What's the electron source? The lone pair on the oxygen. Do you really want to make a bond between bromine and oxygen? There's a reason you haven't seen it. Okay? That's not a good bond to try and make. Okay? So does Br2 work? No. So that's off. Okay? We said we did make this more challenging because we don't know what reagents are provided to us. Maybe we actually have the answer right now. Okay? If we backtrack through our possibilities or what we've identified, I'm fairly confident we don't have the answer for the record. Okay? We have HBr as reagent 1 to convert the alcohol to the bromide. Okay? It's a little bit questionable as far as its utility, but it could probably do what we want it to do. We follow that with the acetylide. Great. We then follow that with HBr again. Ooh, interesting. Okay? And we get back. That should potentially set off alarm bells, like we use HBr twice. Like, that's a little sketchy, but yeah, maybe. Okay. How is our reagent 1 HBr different from our reagent 3 HBr? One's 1 and one's 3. Yeah, okay, what's the next thing?
They're reacting with different structures.
And
One's acting in a substitution, the other's acting
in addition, I accept that, and
There's more in the third reaction?
I need more in the third reaction. In fact, I need 2 equivalents because it runs twice. Okay, so we could switch this up, and if we looked at it, we could say this is 2 times. So we could say reagent 3, reagent 2, reagent 1. Officially, reagent 2, we should put the counter ion on there. Sodium, any kind of metal will be fine, and we get the negative carbon. Okay, decent? Okay. So now we get our big reveal where I delete everything, and we can now go through and look at our possible answer choices. Of course, they're all grayed out, but those aren't too bad. We can see those. So sodium hydroxide, did we use that? No. NaC, what is that, a double bond? Oh my God, I can barely see that. Can you see it better? Yeah, it's a little better. There's a triple bond.
Yeah, it's a triple.
Did we say we needed that?
Yeah.
Yeah, that was our step 2 reagent. That would be a good thing to put in there. Okay, HBr,
That's reactant 3.
that was one of our reagents. Br2, we said wasn't a good idea. H3PO4, okay, what would H3PO4 do? That's an acid. It would just protonate our alcohol and ultimately not get us what we wanted. So that was actually one of the dead end steps we had. Other reagents we've got, okay, sodium with a triple bond and a carbon. Ooh, now we got to be careful. Did I screw up and forget to draw an extra carbon? Because we have 2 of those triple bonds. We have one where it's a hydrogen. Everybody see that? We have one where it's a hydrogen and one where there's a CH3. Okay? So let's scroll back up. What should be on our triple bond? Should it be an H or a CH3? Should just be the H. Okay? So good job recognizing we need the triple bond as a potential reagent. We've got it in the wrong slot. It should be in slot 2, not slot 1. But it needs to be the one with the H, not the CH3, which does bring in a potential issue. Triple bonds are notoriously challenging to track carbons with. Okay? So if you see a triple bond, what I would immediately go through and do, 1, 2, 1, 2, 3, 4, 1, 2, 3, 4. So I now know how many carbons went through there, and I know I'm not adding yet another carbon into that picture. Does that make sense? I would do the same thing with my reagents. So counting those carbons can be very, very, very powerful to ensure that you don't make a mistake. We have CH3CH2Li. That would be a negative carbon, okay, which is possible, but then that negative carbon would have to attack a positive carbon. We didn't really have anything like that within our system. Okay? This is where tracking those positives and negatives and what changes were there come in handy. Okay? And then the last one, PBr3. We didn't even talk about PBr3, so that must be utterly nonsense. So if we align based off of what we talked about, what did we say we could do? Reagent 1, we should say is? HBr, because we've got that, right? Reagent 2, we said was? NaC triple bond with the H, not the CH3. And then the last one we would say was HBr. Okay. And so those would be wrong. Okay. And we might try and click and submit on this, but I think we're going to encounter a different issue, and you may have to address it because maybe you're trying to do this. Can you put HBr in twice? What? I can only put in HBr once. Once it's used once, I'm done. I can't use it anymore. Okay? Which of those two spots was critical for HBr? The last one. We had to have HBr for the last one. What does that mean? While we may have liked HBr as a potential reagent for this, there's something else that SmartWork is looking for. Why? Because there's something better. HBr does not do a very good job with that particular reaction. Okay? That reaction, because you generate a really good leaving group, wants to run SN1, but as a primary substrate doesn't function very well as SN1, and it runs as a very, very slow reaction. Okay? So what we're talking about is reagent 1. We were talking about converting that OH, that alcohol, into that structure. Right? So we need a reagent to do that. Okay? And maybe we're wrong, okay? And we don't want to bring in that bromine, but we know that reagent or that reaction works. So at this point, what we should be going back and doing is looking at each of those reagents and deciding, could this work? Does it have the components that would allow me to do this? And then do I understand what that reagent does? And if I don't understand what that reagent does, what should I do?
Write it out.
We could try writing it out. What else? Look it up. Look up the reagent to figure out what that reagent does so that you understand what's going on with it. I love the idea of writing it out, but some of this, you're learning new reagents, you may not know how it works. Okay? So could NaOH be a potential ringer for this? No. So that's off. HBr we already crossed off. How about the triple bond with the sodium?
No, we're already using it.
Oh yeah, we already used that, so we got to get rid of that. Br2,
We said
we talked about it, and that doesn't do that reaction. H3PO4, why no? True, it's an acid. Why else no? What? What does the heat do?
Well, it makes 5 bond, or not make that 5 bond.
Okay. I accept that. What's another reason why it's not a valid reagent for this reaction?
You're just promoting DOH.
What's another reason it's not valid for this reaction? Your explanations are okay, but there's one that's screamingly flippin' obvious. Look at what you need. You need a bromine. H3PO4 doesn't give you bromine. That makes no sense as a reagent. So that's off the list. We had a couple down below, so we could take a look at those. The triple bond thing already had an extra carbon, still no bromine, so that's off the list. CH3, CH2Li doesn't have bromine, off the list. That leaves us with PBr3.
Just out of curiosity, why would it need bromine? There's no bromine in that, at least in this product, this reaction, there's no bromine.
So when we look at it, so that becomes the next thing. When we went through and did it, we found a pathway that involved bromine. Did it have to be bromine? No, it could have been something else. Okay? But it needed to be something that didn't have other chemistry, like the alcohol has that acidic hydrogen. So what other atoms would work there other than bromine? Chlorine, iodine. Go through all the other reagents. Did you see chlorine or iodine in any of them? No. Okay? So we could still use that same logic. So you're right, absolutely. It didn't necessarily have to be bromine, but it needed to be something that limited all other potential chemistries. That's really only going to be our halogen, so we're stuck. Right? If we go through all of our lists, the only thing we've got left is PBr3. Does anybody know how PBr3 reacts?
It goes from OH to
I didn't say what it does. I said how it does.
a BR leaves and PBr2 attaches to the oxygen. And
Okay,
creates
so now
bromine.
we're trying to process it. Okay, so that's good. It sounds like a couple people may have recognized this reagent and may have seen the video on it. If we looked at a Lewis structure for PBr3, we get something like this. Okay, and we've got our starting material, our alcohol. And if we looked at mixing those two things, what might stand out to you and be like, oh my God, this does not look promising? Because I look at it and I go, this does not look promising.
There's a lot of electrons.
There's a lot of electrons. This looks like one electron source reacting with another electron source, and we said, that doesn't happen.
I mean, and it seems to be stable already.
It's neutral already. Like, there aren't even charges in there to, like, help me out. Okay, so we might very well go through, I don't understand how this reagent works, which is cool. That's exactly why I said this is one of the things you should do is look it up if you don't recognize the reagent. Okay? On top of which, how many times have we seen phosphorus react?
Very few.
That's a more appropriate answer. It's not very few. It's none. We haven't. Okay? So it is an entirely new structure. Okay? If we look at where phosphorus is on the periodic table, it's in the third row. What's special about the third row? Shit gets crazy with the d orbitals. Okay? D orbitals come into play and just mess with our ability to process it. This is why organic chemists stay happy in that second energy level and then ignore everything else. Because it starts to get bizarre and like, what the hell's going on? That's nuts. I don't want to look at it. Okay? Phosphorus, with that d orbital possibility, has the potential to do what?
Can it exceed its octet?
It could expand its octet. Those electrons can come in, sorry, that's supposed to go to the phosphorus. Okay? That typically we wouldn't say is really allowed, but it is allowed to make that kind of coordination. At the same time, we have great leaving groups. The leaving group can kick off. And what we would generate then is the connection between the phosphorus I'm not going to worry about all those lone pairs. Okay, and that oxygen. That oxygen is now positively charged. Does it want to be positively charged? No, so what does it do? It leaves. It takes the electrons and shares even more electrons with the phosphorus. Okay, this forms a phosphorus oxide product. The phosphorus oxide is stable. It does exceed its octet. Okay, those other bromines have continual possibilities. It can continue to go through and react and swap out those other bromines, and we end with some phosphorus oxide nastiness at the end. Okay, but that as a leaving group, we have the other bromide that was kicked out. What can that bromide do? That's what sets up our reaction, and that's where we get the substitution.
So why wouldn't the oxygen just get rid of the hydrogen like it does in the other scenario?
So it can, and I believe it absolutely does at some point. It's a question of when it gets rid of it. Ultimately, even then, the connection between the oxygen and the phosphorus, okay, is a better system than the connection between the oxygen and the carbon. So regardless of the state of that hydrogen, we still preference the electrons to the phosphorus than we do with the carbon, which means the carbon-oxygen bond is now weaker. Okay? Why? Why would we preference the bond between oxygen and carbon than oxygen and carbon? Or sorry, why would we preference the bond between oxygen and phosphorus instead of oxygen and carbon?
More willing to donate its electrons to oxygen? Not that.
So there's an interesting theory. What are you saying?
Well, I'm
Okay.
saying it's more willing to give away its electrons, and oxygen wants electrons.
Okay, so the difference in electronegativity between oxygen and phosphorus is larger, which means oxygen would be happier just chilling with all its electrons. Okay, that's a decent explanation because we're talking about carbon versus phosphorus. Phosphorus is willing to say, hey, oxygen, you can have some of those electrons back. Okay, that's an electronegativity argument. There's another argument.
And also because phosphorus can exceed its octet, so it's willing to take more.
Kind of has to do with that. If we look at the orbital, so if we had that happen, we'd be making this oxygen-phosphorus double bond. And at that potential scenario, we might be saying, isn't that a stronger bond than with the carbon? And if it's a stronger bond, isn't that worse than with the carbon? So it is an electronegativity thing, and there's another thing going on with that. To make that double bond, what orbitals are we using?
D orbitals.
Not d orbitals. Because we're making a pi bond, we use p orbitals. Okay, I'm going to ask the question again. What orbitals are we using? I'm going to ask the question again. You're not being specific enough. What orbitals are you using?
Above, below?
What p orbital on oxygen are you using? What p orbital are you using? And then saying s isn't going to work. Are there different p orbitals?
This is a hybridization question.
It's technically not hybridization, but yes.
This doesn't have to apply.
It's not even, p, x, p, y, p, z isn't a bad idea, but if we're going to make the overlap between those, okay, it's going to have to be the same one, x, y, or z. So good, you've at least differentiated that there's different p orbitals. Awesome. There's another differentiation between p orbitals.
Is it like 2p3, 2p2, stuff like that?
Where are oxygen's electrons? They're in the 2p orbital. Or sorry, wrong emphasis, in the 2p orbital. Where are they in the phosphorus? The 3p orbital. What happened to the orbital overlap between a 3p and a 2p? It's less, because the 3p orbital is larger, so you get less perfect overlap, which means the oxygen isn't as willing to share with the phosphorus anymore. And instead, what you could get is the oxygen holding on to its electrons and the phosphorus chilling out there, technically not with a positive, I think, because it still has the lone pair. Okay? This is fun. This is what's known as a yllid. Yay! Okay? We don't really need to know about ylids yet. That's our next unit. Okay? But we will talk about the yllid structure, and it has a lot to do with the overlap of the phosphorus with third row elements with second row elements. that overlap of orbitals is weaker and therefore is a weaker bond. Okay? That can help have polarize that bond even more to make that oxygen phosphorus structure a really good leaving group. Hooray! So what does this mean for us? PBr3 is our reactant 1, which converts the alcohol into the bromide. Reactant 2 is the sodium triple bond with the hydrogen. And then reactant 3 is HBr. Now we've got all the species lined up where we can set that up. Okay? These kind of questions where you're given a selection of reagents are designed to help you think through what those reagents are. And if you don't know what they do, that's okay. You get 2 options. Draw them the hell out. If they're simple reagents, if they're involving phosphorus, you may be like, well, what the hell does this do? That's okay. Don't draw it out. Look it up. Figure out what it does and be like, is that what I wanted it to do? Yeah? Okay. Now I need to remember that that reagent does that. It's trying to reinforce that process of learning those reagents and when to use them. Get it? Fun question. You getting it right now? Yeah, okay. Just checking. Next question.
It's 4 under MC4.
Multiple choice. Oh, I do think I know why this question's there. My consternation and pause was that this seemed out of place. But it is an okay should I make that bigger? That's pretty small.
Is that question supposed to be there?
Say again?
Is that question supposed to be there?
I think it is okay. This goes back to, okay, number one, I would argue it's fine because you should know how to do this from OChem 1. Okay, so it's a review question in that respect. Typically what we're looking at here, though, is those carbonyls, and those carbonyls are going to this question will show up again probably in exam 2 and in exam 3 and on the final, okay, in multiple different variations and styles, not necessarily just ranking, but what's the correct reagent to use. Knowing how these things react according to their acidity becomes very, very important. Okay, so let's frame this from our OChem 1 knowledge. If we're talking about ranking acidity, what are we talking about?
How willing it is to donate the hydrogen.
Okay, so we're looking at a proton donor. So if we're looking at HA as an acid, we're looking at producing H plus and A minus. And if I wanted to compare that to a different acid, we'll call it a green acid, HA, H plus plus A minus, how would I decide which of those acids was the stronger acid, red or green? What could I look for?
Differences in electronegativity.
Where are you looking for the difference in electronegativity? Because I look at those reactions and I see 3 different things.
The bond between the hydrogen and whatever other chemical.
So you do have the potential for looking at differences in electronegativity here. Generally speaking, for me, I think that's hard to do. If you find that's easy, that's okay. But what you're talking about doing is starting to use your rules of differentiating reactivity. Okay? And this is where electronegativity is one of those rules, but it's dangerous to jump straight to electronegativity. Because what's more important than electronegativity? Charge and size. So if you only jump to electronegativity and you're making that difference here, you're ignoring charge and you're ignoring size. Theoretically, you're not ignoring charge because they're both neutral. But how do you evaluate size? Well, is it the size of that whole molecule? What is it the size of?
The acid. You know
That's
what I
the
mean?
whole molecule.
No, you know what I mean, what the A stands for.
Ah, it's the A. So why are you looking at a structure that is not A? It's HA. So if you're going to evaluate and use charge, size, electronegativity, resonance, induction, and oh my God, I hope I never have to do it, okay, you should be looking at the conjugate bases. Because there it's standing on its own. And now I can make a raw comparison between the green A and the red A. And now I can say, what's their charge? Well, they're both charged. I can say, what's their size? I can look at the atom holding the charge and say, what's the difference in size? It's a cleaner approach. Not better, cleaner. It's a different approach. Okay? So we can effectively rank our acidities by looking at these and using our, for lack of any better acronym, we'll just call it our CARIO acronym.
What did you call it before?
I don't have an acronym for it because the words that I use for each of those turn into friggin' nonsense.
The only one I remember is
Right.
shit. That's
I
the one
got
remember.
charge, size, electronegativity. I'm even using a resonance, induction, and then the O, which is the O carb, because I don't know what the O stood for in CARIO. That doesn't look like a really cesarean, cesario. Like, that doesn't make any sense. Okay, but that's what I would be referencing because this calls to attention each of those. In the case of CARIO, it combines size and electronegativity into one thing. They have different weights behind them. If you put them in one thing, it could be easy to swap them back and forth. Okay, and then O, someone told me maybe stands for orbitals. Yeah. That's okay. I like my O as an O carb because there's a whole bunch of other things that could contribute to it. Substitution patterns, okay? Tertiary versus secondary versus primary, tetrasubstituted, trisubstituted, disubstituted, cis versus trans. All of those would fall in that kind of O category, okay? Which isn't necessarily orbitals. In any case, you could rank based off of looking at the conjugate bases. The more stable the conjugate base, the more likely that reaction happened. So if we look at these, I'm going to say the red one looks a little bit larger. We okay with that? Okay, there's a little head shake there, so we'll make it. I'll say the red one looks a little bit larger. Okay, because it's a little bit larger, that makes it, based off of size, more stable. And because it is more stable, this reaction, the red reaction, is more likely to happen, which means there's a larger concentration of H+, which means HA was the stronger acid. Okay? You can go through and look at just comparing the HAs, and not just the way you were saying, because you were still trying to use this. I find it difficult to do that. Okay? Some people can pull that off. I just don't do that well, so I don't recommend it. But you can still look at the HAs. How do you look at the HAs? I think two people should be getting this right.
Oh,
You would have memorized your pKa's for individual acids. Okay, that would allow you to predict that. Okay, I'm hesitant to recommend memorizing pKa's because when we move to this particular scenario, what did you memorize for your pKa? Okay, you might very well have memorized that the hydrogen that is, don't shoot me for this, it's technically alpha to the carbonyl. If you understand alpha and beta and all that, sorry, this is our alpha to our carbonyl. Okay, that hydrogen has a pKa of about that of water. Sits about 15. Okay, so I could go back and look at this and say, oh, well, this one has a pKa of 15. And so does this one. And this isn't good. So does this one. So what did the memorizing of pKa's get me? Nowhere. Okay, so I don't necessarily recommend memorization of pKa's and instead would push you to the conjugate bases. How do we figure out our conjugate bases? Well, draw the freaking conjugate base. So for the first one, it should be relatively straightforward, just putting a negative carbon. For the second one, okay, the second one becomes more challenging. Why is it more challenging?
Because the two carbons aren't the same on the
Ooh, the two carbons aren't the same, which ultimately is actually saying the hydrogens are not the same. Which of those two hydrogens do you think is more acidic?
The one connected to the bromide.
The one connected over on the bromide, so we should be putting our negative over there. Why is that hydrogen more acidic? Why would I rather have the green negative as opposed to the purple negative?
Because the green negative is connected to something that's more electronegative than itself.
They have the same charge, they'd have the same size, they have the same electronegativity, they have the same resonance. The green one is closer to an electronegative element. There's more inductive effect on the green one, which is what's stabilizing it. It's drawing the electrons into the structure. That's why that green one is better than the purple one. Last one, similar to the green one, is also hard. Which hydrogen do we remove?
The one in the middle? No.
The one in the middle.
Wait, but wouldn't the electronegativity effectively cancel out because it's the same forces going in opposite directions?
So if I'm here as a negative, and that negative is getting pulled two different directions, am I more negative or less negative? If I'm getting pulled in two different directions, do I have more electrons or less electrons?
Neither, you're the same.
It's less.
I have less electrons. Those are being withdrawn away from that center atom. Okay? So if we look at dipole moments, we're not looking at dipole moments, we're looking at the ability to do resonance. Okay? If we look at this, I can do resonance here. So I draw one resonance structure. When I look at the purple one, what can happen? I can do resonance here, and I can do resonance over here.
Creating a greater partial negative.
Okay? So technically a smaller partial negative, a more stable negative, which means stronger acid. Okay? Believe it or not, as we talked through that, we've already discovered the answer.
So
3 is going to be more acidic than 1 because it has two potential resonances, where 1 only has one potential resonance. Okay? 2 should be more acidic than 1 because
induction.
there's an inductive effect that 1 doesn't have. 3 should be
Most acidic.
more acidic than 2 because,
It has more resonance structures.
but this one has more induction.
Well, resonance is above.
Shifting the eyes, yes. Resonance is more important than induction. Okay? So our ranking for this, okay, most acidic should be 3, followed by 2, followed by 1. I didn't actually provide the explanations on those written down, but we talked through them. Okay? Ideally, if you were doing this for paper homework, that's what you would write down as well, noting those structures so you could see those things set up. Make sense? Does that work for you, Ivan?
Yeah.
And then we'll see if I screwed up the multiple choice. Looks cool. I didn't screw up the multiple choice. Sometimes I goof the direction of the arrows, but here they're all internally consistent. I try to avoid that, but sometimes that happens. So in this particular case, our answer is C. Okay? And it's touching on all of those individual aspects. We get resonance, we get induction, we get more resonance. So it's looking at all of those individual pieces out of Cario. Okay? Or I think I'm Scario. That one's kind of cool. Scario. Scario. You don't watch the videos again anyway. What's up? Okay. Next question. Are we good with that one? Guaranteed I'm going to get a value. Someone in the evaluation would be like, such an idiot. He kept saying Scario all class period. It's fair. Okay. Next question. this one is brutal. So, this particular question has a whole lot of junk going on within it. I'll tell you, I've seen things like this before, and typically what I do is just start picking one and just see what happens. Right? That I just found the easiest approach for me for going through and doing it. I'll see if we can't do it more elegantly here, but I honestly don't know. Right? So if we go through and look at the products, so we're talking about what would produce this mixture of products. Okay? First thing we would need to address is what was reacting, what was the reagent that's going through on this. A couple approaches to that. One is you cheat and you look at your answer choices. When we look at the answer choices, what was reacting? A pi bond. Okay? So what we're doing in this case in particular is an addition reaction. Okay? And we're adding something to a pi bond, so we get the loss of a pi. Okay? What things are we gaining? Okay? As we've addressed before with additions, it's 2 sigma. When we run an addition, what are those 2 sigma going to be? Okay. H and OH okay, are going to be our 2 sigma. How do you know it was H and OH?
Looking at both the products.
But if you're just looking at the products, we have to be a little bit careful. You're also looking at all of the answer choices having 2 pi bonds, so you're combining both those pieces. Okay. Perfectly fine, legit on the exam. Ideally, we would try and reason through it a little bit more. We could go through and look at that starting reagent. What does that reagent supply? Say again? What does our reagent supply?
OH.
I want a little bit better than hydrogen. It supplies H plus through the sulfuric acid, and then it also supplies that water, which would be our OH, and that we would somehow then lose that other hydrogen through the course of the reaction. Okay? So that oxygen would likely be our source of electrons, and our hydrogen would be our positive. Okay? We could pick that up from the reagent, which would again suggest that more than likely we started with a pi bond instead of just cheating and looking at our answer choices. Okay? The next thing that I would try and go through and do is recognize the charges that we're evaluating. Okay? I've got the hydrogen being positive, and I have the oxygen being our negative, which means in my answer, that carbon should be positive, that carbon should be positive. Okay? Now I was trying to track down where the hydrogen went. Okay? So where was the hydrogen in either of those cases? Not going to lie, I was hoping this was going to be elegant and beautiful. I'm not seeing it.
On the other side of the pi bond.
So you said other side of the pi bond, which structure are you looking at, left or right? Left or right structure?
Left.
The left structure. So other side of the pi bond up here? That's where your hydrogen went in?
No.
Okay. Then you're the one that told me. I'm just trying to draw it. What other side of the pi bond?
There's presumably a pi bond which would have a positive and a negative then, so whichever. One of the carbons that's connected to the positive one. One of them, I don't know which one. The left.
Oh, okay. So you're saying kind of here is where our hydrogen potentially went?
No.
Over here? Okay. Why do you not like the one with the pi bond?
I mean, because it doesn't feel right.
It wouldn't exceed the octet because you would backtrack out, and what would that mean? Your starting structure would have double bond.
Right next to double bond.
Bingo.
Just kind
Okay. That looks a bit sketchy. Add the fact that you're then also confined in a cyclohexane or hexene type structure. That's going to be pretty unlikely. Okay. So it makes more sense to put that hydrogen over there. Okay. So if that's your argument, then the starting material you're kind of postulating here would be this one. Right? Okay? So if that's what you're postulating, that's fine. We'd have our hydrogen react, put the hydrogen on there, we'd have the carbocation at the tertiary spot. Then what could happen? The water could come in and attack. There's our OH. What else could happen?
The hydrogen would protonate.
No.
The sulfuric acid.
No.
Okay.
Keep trying. It's good. What else could happen? We put that hydrogen on there. There's our positive charge. What else could happen?
The OH would
OH could come in. That produces one of our products. What else could happen?
It could react with the other pi bond.
Resonance?
Good confidence there, by the way. Okay. If we did that, we got resonance. We're allowed to do resonance. And now what could happen?
The OH can go on that.
The OH could go in. Okay. Would that produce our far right?
Yes.
It clearly produced the first one, right? Okay, because that made sense. Okay. So what does that mean?
That is the right answer.
Well, dang, that worked pretty well. I don't know if you lucked into that or just that spontaneously worked. That seemed pretty impressive.
You saw the teacher.
Okay.
I'm just that good.
Okay. So in that case, we picked out where our positives were. We picked a structure for our product. We said we had to add H and OH. So let's just assume that it's that pi bond. Draw that out and now test it. Run the real quick test and see what's going on. Should it have reacted with the other pi bond?
No,
Why not?
because the other one has a more stable carbocation due to more substance.
It has to do with the stabilization of the carbocation. That tertiary or the bottom pi bond is more likely to produce a more stable carbocation than reacting the other pi bond. So when we're producing two products, it isn't reacting with different pi bonds. It's reacting with the exact same pi bond. And that becomes one of the challenges within this question. Is we see two products and two pi bonds, and we assume that it's reacting with either pi bond. That's not true. It's reacting with only one pi bond. The other pi bond is just moving around that reaction. If we go through and look at our other our possible products, okay, we could have done the OH, and then there's our positive. What could happen? We could do resonance with that one, which would then place our positive up here, which would then mean, whoops, what did I do? We would put, sorry, not the positive there, our positive here, no resonance, that's it. That's all we'd get, okay? We could make the argument that maybe it's more likely to put the positive out here, okay, and put the hydrogen into this spot. Why is it more likely to put the positive out there? You want to save the day again, Caden?
No,
You got it.
I don't think I do.
I guarantee you do.
Resonance.
Yeah, I wasn't going to say that.
You already said it. You just had to repeat yourself. Okay? There's a resonance stabilization of that secondary position that's better than putting it on a tertiary without resonance. Okay? But if we'd done that, that gets an OH here and an OH up here. Is that what our product shows? No. So that doesn't match. Okay? We could try and brute force. So, and this is what we're doing now, is brute forcing. I'm just going to start guessing at these. We could put H and then OH. There's no resonance. Okay, so we aren't going to see any shifts. You might see a hydride shift, but is there any reason necessarily that you should put it in that order? Couldn't it have just as easily gone in this order?
Yeah.
It produces the same stability carbocation. So you get two products right away with that single double bond. Okay? And that's ignoring the fact that we also have a rearrangement that could introduce a third product or potentially a fourth. So B is just going to get us a crap ton of products. I only want two. So B doesn't make sense. Okay. D we already did. Okay, we could go through and look at C. C, we at least have resonance here, so it's going to be more likely to put a positive here or here to begin with. We're going to get both of those as possibilities. Okay, which means I could get my OH up here or here. Okay, if I did resonance, okay, if we start with the blue positive, we could get resonance, which then means I could get an OH over here as a third product. Or if I did the red one, I could do the resonance and I could get my OH over here. That's 4 products, and that, again, doesn't address the fact that we would also get a rearrangement because we shifted the carbocation to within rearrangement distance. So structure C gets us like 6 or 7 products. Okay, kind of makes sense? So within this, if we can break down what changes are happening and then start looking at the information we've got, okay? It's hard to nail down the hydrogen because hydrogen shows up everywhere. So we focus on the oxygen, okay? And we could use either structure, but again, pick one and then say, well, where do I think the hydrogen could have gone? Okay? You pick to the left. If you were wrong, what happens?
I'm not often wrong.
If you're wrong, what happens?
You try the next structure.
You would try the next option. Okay? Maybe what this starting structure was the one that resonated and things have shifted around on you, and that's why it's harder to see what's going on with it. Maybe it's not. Okay? So you would start with that and see what happens. If it looks like it's leading to something useful, great. If it looks like, I don't know, try the other structure and try and place the hydrogen on that and see where that would take you. Okay? And if you don't like those options, then we've got the last one. Just pummel the living bejesus out of it and try everything. Okay? Pick a random starting structure and just try it. See what happens. Kind of make sense? You good? Next question. Please say you don't have a question about that I just deleted.
Oh, no.
Okay, that's good.
I was reading the 11,
Oh, okay.
because I was like, why is it bolded? But,
Okay, why would this be bolded?
as we talked about it.
Okay, as per the discussion in lecture. So when we talk about Diels-Alder, there's lots of things that we could talk about things changing in Diels-Alder. Okay, which of the following things must happen or need to happen in Diels-Alder?
All the above.
Okay, so you need to break all 3 pi bonds? Yeah? Okay. Fully accept? Accept the challenge. Here's this structure, right? I'm going to draw it over here. Ready for me to redraw it? Is what I've drawn and the original structure the same thing? You're saying yes. Everybody else is saying no. So let's see what wavelength you're on.
Residence.
It's resonance.
Just not where the electron, like on the bottom one specifically, the electrons would go on the most outer one, most likely. I mean, just given the starting structure of that.
Given that starting structure, there's nothing wrong with that. What happened? I took these electrons, put them there. I took these electrons and put them there. This is a resonance structure. It is one and the same as the starting drawing. Do I have any pi bonds? No. So you're going to tell me to move from one structure, that black structure, to my red drawing that I broke 2 pi bonds? They are one and the same. Did you break any pi bonds? No. Well, you didn't do the Diels-Alder yet. Fair enough. So let's take a look at this one. What do you think I'm going to draw for that one?
Residence.
Resonance. I'm going to draw resonance, and here you go. Boom. There's my resonance.
We formed the 2 sigma bonds.
So if I look at this reaction, I can take these electrons, put them there. I can take these electrons, put them there. And what have I done?
Make a hexane.
The negative and positives around the purple arrows are gone because they're now canceled out. The positive and negative here right? What is the difference between my product and the actual product of Diels-Alder? Nothing. They're just resonance structures. Did I make or break any pi bonds? No. Not a single flippin' one. All I'm evaluating is the resonance structure. I may not like drawing resonance structures with all that charge. You're absolutely right. But that's not relevant. What had to happen? The only thing that had to happen was
Forming 2 sigma bonds.
I formed 2 sigma bonds. Everything else was the electrons just shifting around. Okay? And this becomes useful because if I can boil Diels-Alder down to just forming 2 sigma bonds and not breaking 3 pi bonds, or forming 1 pi bond, because that is now 3, 4, 5, 6 different things. If I want to think about a mechanism, how many possible mechanisms can I get with 6 different things happening?
A lot.
That's a lot of mechanisms. I get to run all 6 things at the exact same time. I could do one of them first, then the other 5 at the same time. Or I could do all of them individually. Okay? That's a crap ton of stuff going on. That's going to be a really hard mechanism to try and explain and understand and learn and design an experiment about. Okay? But if I can change how I shift and think about my individual drawings and not consider them as static, solid things and recognize that my electrons, some of my electrons have the ability to move and float on their own, I can change my understanding and vastly simplify the overall system. In that vastly simplified system, I can now ask, did I form those 2 bonds at the same time, or did I form them in steps? That was the whole point of lab.
I
Right?
still don't have our answer. I mean, I don't know if we have our answer.
You have an answer. It's just the question of how it went through and happened. And of course, as far as the lab goes, which is now a separate can of worms that we're opening, if we go and consider the lab, the point of the lab was to figure out whether it was steptized or simultaneous. Do we have evidence to suggest one versus the other? Did we have evidence for any rotations? No. If you have no evidence of rotations, what does that suggest? It was simultaneous. Did you answer the lab's question?
Sure.
Yeah. Could you ask other questions? Yes. Does the lab answer those other questions? That's where it gets sketchy. Okay? And that's one of the things that's, I think, interesting with the Diels-Alder, but also why I'm trying to pare it back to get you to think about just focus on the points that we're trying to solve. Where do we have evidence?
Does this mean that all Diels-Alder are simultaneous?
Which then introduces the next issue, okay? Because students will do this. They'll go, oh, I proved that the speed of light in my experiment was 4 miles an hour. Therefore, all science is wrong and I am right. No, that's not what that means. Just because your experiment showed the speed of light was 4 miles an hour doesn't mean everybody else was wrong. That means you were wrong, and you should figure it out by retesting your experiment. Do you get to retest your experiment? No. Okay? So regardless of what other conclusions you can make from your experiment, that doesn't mean those conclusions mimic out to the real world. Ideally, they come into alignment. That's not always the case. So don't start making those jumps. But what you would do is say, this is what I saw. This is what my evidence suggests. Does that align with the real world? Cool. I'm contributing to science. Does it counter what's happening? Cool. I'm also contributing to science. I should figure out why my stuff is countering it. Right? Which means do it again. Do you have time to do it again? No, so then don't worry about that part. Kind of get it?
Well, just this makes me ask the question, does our results from lab go along with the real world results?
Depends on the question you're asking. If you're asking about stepwise or simultaneous, yes, I think it does. If you're asking about endo or exo, no, it does not. And I don't have good evidence there, and I'm finding more papers and background information that is also very strange, particularly for the fumaric acid. I can pull that up in a second if people really want to look at it. Do we have other questions? You got nothing.
You want a would you rather question?
Would I rather answer a question about Occam than that? Probably, but okay, let's go for it. What do you got?
Would you rather have bones of glass, or would you rather have or sleep in a bed of centipedes for the rest of your life?
Sleep in a bed of what?
Centipedes.
Bones of glass.
I think I'd take the centipedes. Here's the
You
question.
didn't say if they had to lie to dead.
Yeah. Well, if I lie on them, they're dead. Here we go. Here's a new question. Which of the following molecules would be expected to scavenge radicals well? Yeah, everybody freaks out at this question.
Aren't oxygen able to do it well?
What's that?
Isn't like oxygen able to scavenge oil?
Actually, oxygen is terrible at scavenging
I mean,
oxygens.
look at C. That looks like.
It produces tons of oxygens, or tons of radicals. So oxygen is very dangerous.
Let me see. Look at that repeating.
What about the nitrogen?
Same thing in that.
Hydrogens really don't do much either.
Nitrogen.
Nope.
No.
The pi bonds?
Does carbon do something?
Where are the radicals coming from? How did you get the radical? What did you do to cause the radical to come into existence? How did you break that bond? With light. Right? So if we're going to try and scavenge radicals, what we're trying to do is limit some of that production, number one. So what we might do is use molecules that absorb visible light. What absorbs visible light? What absorbs any light? Pi bonds. When you conjugate multiple pi bonds together, what happens? You shift the spectrum. Right? This goes back to our UV Viz stuff back in Unit 1. And by Unit 1, I mean not Unit 1, I mean OChem 1. And Unit 2, when we talked about spectroscopy. When you conjugate enough pi bonds, the energy between the HOMO-LUMO gap shrinks. And as the energy shrinks, it shifts into the visible range. So if we look at this purple dye, or red dye, whatever you want to call it, okay, of my shirt probably comes from an organic compound that has been embedded into the material. The same thing with every single color shirt that you have. It is probably due to an organic dye that has been put into the material to absorb light. The color that you see is in the light that was not absorbed. So black shirts have tons of dye molecules because they're absorbing all the light, right? Which is why they appear black. They aren't reflecting any colors off. Right? When we talk about radicals, if I want to scavenge them, what I'm trying to do is grab them and hold them, right? Neutralize the reactivity. Well, if I just have that single electron sitting on a single atom, does that neutralize the reactivity? No. What do I want to do? Allow that electron to
Make a bond.
move. How do electrons move?
It's a complex question.
It's a straightforward question. You're just making it complex.
Go towards.
What bonds do they move through? Pi bonds. And when electrons move through pi bonds, we call that
Resonance.
resonance. So if we can form a radical in any one of these molecules, can that radical move through the entire structure? If it moves through the entire structure, this has now become less reactive, because instead of being in one spot where it can now be stabby and dangerous, it's across 20 different spots, all simultaneous. So which of those molecules would allow for lots of resonance of said radical? A. Guess where A is found? Actually, I think A is not found where I wanted to say, but take a look at your sunscreens. And if you look at sunscreen and you look up the structures of a lot of the active ingredients in sunscreens, almost all of them look like structure A. Okay, some version of it. It's just a crap ton of pi bonds. Okay, why? Because what they're trying to do is two things: absorb the sunlight, and if a radical gets formed, they can stabilize the radical by moving that back and forth through the molecule, as opposed to it reacting into your body and getting into your DNA, causing cancer. Hooray. Where's that molecule actually found? I believe that's actually retinol, which is found in your... It is sometimes found in your skin care. Yeah, what was it? Eye. How do we see light? Molecules like retinol with slightly different structures. Okay, and what happens is light comes in, breaks one of those pi bonds. When it breaks the pi bond, what can that structure now do?
Rotate.
It can rotate. So now instead of being a flat, straight structure, it's now bent.
Oh.
That changes how it interacts with the environment, and what does your body decide that is? Color.
You know what? This was a test question, wasn't it? I
It
remember
was.
this being a test question, and it sucked because nobody got it. Not a single human being.
I think it was an extra credit question.
It was an extra credit question, but still, it sucked. I hated it.
Yeah. Well, because it's pushing the stuff that is very challenging, which is molecular orbitals. Then yeah, it's neat. Okay, but I'm going to stop the video there.